Okay, let's unpack this. We talk constantly about the AI frontier, and right now, that frontier is really defined by this relentless race for truly functional long-context reasoning.
It really is.
You see the headlines all the time, right?
Yeah.
Models that can handle 128,000 tokens, maybe even 200,000. But here's the critical insight we need to start with. Merely expanding that context window is often just making the swimming pool bigger.
Yeah.
It doesn't mean the model is smart enough to efficiently, swim from one end to the other, find all the scattered clues, and then synthesize a coherent answer.
It often just leads to a more sophisticated kind of information overload. We've seen it time and again. Memory capacity is only half the battle.
Right.
You get these models with enormous context windows that still suffer from that classic lost-in-the-middle syndrome. They can technically hold the data, but they can't effectively reason across massive, disparate pieces of information that require, multi-step logic.
So our mission today is to analyze the systematic solution proposed by Alibaba's Tongyi lab. We are diving deep into QwenLong-L1.5, post-training recipe for long-context reasoning and memory management.
And this is fundamentally about refinement. That's the key word here.
Yes, it's not about new architectures, but about the sophisticated training optimization that happens after the base model is built. It's sort of like the finishing school for LLMs.
And the resulting performance jump is truly remarkable. This systematic recipe achieves long context reasoning performance that's comparable to, and in some areas even exceeding, flagship proprietary systems.
And they're not shy about who they're comparing themselves to.
No, the team explicitly referenced challenging models like GPT-5 and Gemini-2.5-Pro, and they did it all by focusing on this highly disciplined post-training optimization, specifically advanced reinforcement learning from human feedback, or RLHF.
The numbers are what really grabbed our attention. QwenLong-L1.5 surpasses its own baseline model, and that baseline, the Qwen330D A3B thinking, is already formidable.
Very capable, yeah.
By an average of 9.90 points across all the long context benchmarks. But here's the shock factor, and the evidence that this is a fundamental intelligence leap.
This is the part that matters.
The largest gains are concentrated precisely where the task complexity is highest. On the multi-hop reasoning and complex retrieval benchmark, MRCR, the model gained an astounding 31.72 points.
Wow.
That's not an incremental adjustment. That feels like a new capability is being unlocked.
It absolutely speaks to the critical gap they identified. I mean, historically, long context research has focused primarily on architectural innovations, things like linearizing attention or, tweaking pre-training objectives.
Right, the plumbing.
The plumbing, exactly. The missing piece was a mature, end-to-end post-training recipe that systematically refines the model's high-level reasoning and synthesis skills. It's about treating the context window not as a storage bin, but as a strategic information space.
So what specific foundational problems were holding back existing long-context models that this new recipe manages to solve?
There were 3 specific interconnected hurdles, and the L1.5 recipe provides a unified solution for all of them. First, the data challenge.
Okay.
They noted the severe scarcity of truly high-quality, challenging data. And we're not talking about simple keyword retrieval, the famous needle-in-a-haystack task.
Right, not just find this fact.
No. We need data that actively demands complex, verifiable multi-hop reasoning and synthesis across widely distributed documents.
So the challenge isn't just find this fact on page 50, it's connect fact A on page 50 to fact B on page 100, and then use both to draw a verifiable conclusion C.
Exactly. That difficulty has to be baked right into the training set from the start.
Okay, so that's problem 1, the data.
Problem 2 is technical instability. Specifically within the reinforcement learning phase, training a massive model with RL, especially on these long, complex, and highly diverse contexts, it often leads to catastrophic instability. The learning signal itself becomes so noisy that the model's parameters just, diverge wildly.
It basically goes off the rails.
Completely. And finally, the third challenge, which is that inevitable architectural wall. Context windows, even the extended ones, like 128K tokens, are still finite.
Sooner or later, you run out of room.
You do. So how do you handle truly arbitrary, ultra-long tasks like analyzing 4 million tokens, which is just far beyond the physical capacity of current GPUs.
And that requires a whole different way of thinking?
It requires a paradigm shift. That's where their memory agent framework comes in, which treats reading as a sequential decision-making process rather than a single massive input pass. The L1.5 recipe unifies sophisticated solutions to all three of these foundational problems.
Here's where it gets really interesting. Let's start with that foundation, the data. When models fail on long context, it's so often because they just weren't trained on data complex enough to force them to use those long chains of logic efficiently. The QwenLong team realized they had to move substantially beyond those simple retrieval tasks.
Yeah. They moved from simple data compilation to what I would call engineering difficulty by design. Their new data synthesis pipeline is, I think, arguably the most valuable innovation in the entire paper.
It's like, instead of just giving a student a textbook, you're designing a curriculum where every single assignment is guaranteed to force multidisciplinary synthesis.
That's the perfect analogy. That's exactly what this pipeline achieves. Instead of relying on slow, error-prone human annotators to write hard questions and then verify the answers across, 100,000 token documents.
Which is a nightmare.
A total nightmare. They built a machine to generate and verify that complexity.
And it does that by systematically deconstructing the source document.
Precisely. They created this robust pipeline that programmatically composes complex, verifiable reasoning questions by breaking documents down into atomic facts and their underlying relationships. The scale of this effort is it's impressive.
How big are we talking?
They increased their core reinforcement learning dataset from a sparse 1.6K samples in the predecessor model, QwenLong-L1, to a really robust 14.1K high-quality samples in L1.5.
Wow, that's nearly a 9-fold increase in the core training data. And I'm guessing the complexity went up too.
Massively. The average input length jumped from around 11,400 tokens to over 34,200 tokens. So they aren't just adding more data, they're ensuring the data demands much, much deeper engagement.
So how do they do it? What are the techniques?
They use 3 specific, sophisticated techniques for synthesis, each targeting different cognitive demands. The first one focuses on in-depth multi-hop reasoning QA, and it's guided by a systematic knowledge graph.
Wait, hold on. How do you use a knowledge graph effectively on unstructured documents? I mean, doesn't that assume the data is already organized in some way?
Not initially, no. That's the first step. They first extract subject, predicate, object triplets, the fundamental fact, from documents across all these diverse domains.
Like Alibaba as a company, or the CEO is so-and-so.
Exactly. Then they stitch all these facts together to form a complex cross-document knowledge graph. This KG is basically a giant map of all the relationships in the data.
Okay, so they've built the map. Now what?
Once they have this map, they start sampling challenging multi-hop paths using algorithms like a random walk or breadth-first search.
So they are essentially using the structure of that map to guarantee that any question they generate requires traversing, say, 3 or 4 distinct steps of logic.
Yes, guaranteeing structural difficulty. But here's the clever part. To ensure the model has to synthesize information across long distances, the path nodes, the critical facts needed for the answer, are deliberately distributed sparsely across multiple separate documents.
So the model can't just read page 2. It has to jump from a fact in document 1 to another fact in document 5, link them through some cross-reference in document 3, and then draw its conclusion.
It forces global context utilization. There's no way to cheat.
And they add an element of linguistic difficulty too, right? I read they obfuscate the key entity information.
Absolutely. The whole goal is to prevent simple pattern matching. They give this excellent example of temporal obfuscation, where instead of asking for a specific year, like 1995, they phrase it indirectly, the year ending with 5 in the late 20th century. This ensures the model has to perform qualitative reasoning and some temporal synthesis before it even attempts to retrieve the fact.
That is extremely clever. Okay, so that's multi-hop reasoning. The second technique focuses on corpus-level numerical reasoning QAA. Why is generating reliable numerical reasoning data so uniquely challenging?
It's because complex calculation questions that span multiple documents are just notoriously prone to manual validation errors.
Right.
If a human has to check a statistical aggregation across 5 different tables in different formats, the error rate is high and the process is painfully slow.
So how did the QwenLong team solve this?
They built something they call a structural tabular data engine.
Tell me more about that engine. That sounds like you're turning a whole document corpus into a functional database.
That's precisely the concept. They parse documents that are rich with tables, they formalize the data schema of each individual table, and then they aggregate all of those into one unified cross-document corpus table.
So once all the information is in this unified, structured format,
You can treat it like a database.
and once it's a database, you can use structured query languages to generate the ground truth automatically.
Exactly. They translate natural language queries into executable SQL statements. Think of them as programmed instructions for calculation. By running that SQL against the aggregated tables, they derive accurate, verifiable ground truth answers all automatically.
So no more manual checking.
None. This allows them to quickly generate these vast, complex tasks focused on statistical aggregation, numerical calculation, and temporal comparisons without needing any manual recalculation.
That's a massive leap in efficiency, and it guarantees verifiability.
Okay.
And the third technique, general long context reasoning, uses a multi-agent self-evolved framework, AMASE. This sounds like the model is evolving its own training curriculum.
That's a great way to put it. MAA is this iterative, quality-controlled process that uses three specialized agents: a proposer, a solver, and a verifier.
How does that work?
They start with some simple seed questions and then iteratively increase the complexity and the diversity of the question set.
But how does the proposer agent know how to generate a question that is harder than the last one? How does it avoid just making the same kind of question over and over?
The proposer is critically conditioned on a history buffer. This buffer contains all the past validated QA pairs.
So it sees what's already been asked and answered correctly.
Exactly. The existence of these successful verified pairs discourages redundancy. By prompting the proposer with this history, they push it to generate questions that are novel, diverse, and cover new semantic ground. It forces this organic, self-improving difficulty curriculum.
Focusing on things the other two methods might miss.
Right, things like viewpoint analysis and long, in-context learning, which complement the structural complexity handled by the knowledge graph and the SQL engine.
I have to pause here because the data synthesis part it's just genius. They aren't just brute forcing better models by throwing more data at them. They're engineering the perfect teaching material.
They really are.
But is this pipeline sustainable? I mean, generating 14,000 samples this complex must be resource intensive, even if it's automated?
Yeah.
Are we just trading human annotation cost for immense computational cost?
That's an excellent critical question, and it speaks to their future research, which we'll definitely get to. But for now, they needed to ensure the data was not just complex, but actually relevant. The paper highlights two crucial filtering steps that guarantee the questions truly enforce contextual reasoning.
Okay, what are those? The first one is the knowledge grounding check.
This is fundamental to eliminating bias. What they do is they temporarily remove the source document, the context, and they test if the base model can still answer the question using only its own vast internal knowledge.
And if it can answer it correctly without the document.
The sample is discarded, because it means the question relies on pre-existing knowledge, not on the model's ability to reason specifically over the long context you just gave it. It basically stops the model from cheating.
It forces the model to prove it used the document you gave out like that.
Exactly. And the second check is the contextual robustness check. This tests for noise immunity.
How does that work?
They expand the context with a bunch of irrelevant, noisy documents distractors, and then they discard the sample if the model's answer accuracy drops drastically.
So it ensures the question and its required evidence are robust, not brittle, to distraction and noise.
It guarantees the model can find that sparse evidence even when the haystack is full of useless data. It's just rigorous quality control, top to bottom.
So they solve the data problem by designing curriculum difficulty and then adding quality assurance. Okay, moving to part 2, we hit the next hurdle. Stability. When you introduce this multi-clustered complex data into the reinforcement learning loop, you said instability becomes rampant.
We're moving from the data preparation kitchen into the model optimization engine room. The core question is, why does training on long, diverse context cause such catastrophic instability, and how did they manage to tame that learning process?
Lay out the instability challenges for us.
They identified two main sources of chaos. The first is what's called distributional drift. Since their highly engineered long context data has all these different problem types, multi-hop numerical dialogue, It has a multi-clustered distribution.
Okay.
So with traditional random sampling, any given batch of data you feed to the model might be heavily skewed toward one specific type. Maybe it's all numerical tasks one moment, and then it's only multi-hop reasoning the next.
It's like trying to train a decathlete, where some days you only practice swimming and other days you only practice the high jump. The overall training schedule becomes wildly erratic and it compromises consistency.
That's a perfect analogy. The second, and I think more insidious issue, is the credit assignment problem. This is really specific to long context generation.
What is that?
In a long reasoning path, the difference between a correct output and an incorrect output can be, well, minimal. They found that for complex math tasks, the correct and incorrect responses had a significant similarity score.
What does that mean in practice?
It means the incorrect answer often had nearly half of the correct information and structure within it.
Wait, let me make sure I understand this. If the model gets 99 correct steps of reasoning right, but then it fails one crucial calculation at the very end, or performs an erroneous final self-correction, the old training method just throws out the baby with the bathwater.
That's the problem. It penalizes all 99 correct steps equally.
Wow.
The incorrect response often contains so many excellent intermediate steps in factual retrievals, but because the final answer is wrong, the advantage signal, the feedback telling the model how to improve, is unstable, and it penalizes the entire trajectory way too harshly. The model has no idea which step was the fatal error, so it ends up damaging the good parts of its policy.
I see. And they're using GRPO, Group Relative Policy Optimization, which I understand is necessary because the gold standard PPO is just too computationally prohibitive for these massive context lengths.
It is, yeah.
But GOPO is highly susceptible to these biases and instability.
It is. So they needed to stabilize GRPO significantly. Their first solution tackles that distributional drift, using something they call multitask stabilization.
How does that work?
They implemented task balance sampling, which replaces the conventional random sampler with one that ensures an equal number of samples from the 5 designated task types are included in every single batch.
So they stopped comparing apples and oranges. Every batch is now a balanced, standardized diet.
Exactly. It stabilizes the distribution. It prevents the model from forgetting skills just based on random data spikes. But they went a step further.
Okay.
They refined the reward signal itself through task-specific advantage estimation. In standard GRPO, the reward is normalized against the mean and deviation of rewards across the entire batch.
But if you mix retrieval tasks, which might have dense rewards, like a simple 0 or 1 score, with complex multi-hop tasks, which have sparse rewards, that global standardization must introduce a ton of noise, right?
Massive noise. So they modified the standardization formula. Instead of normalizing rewards against the entire batch, they normalize against the standard deviation of rewards only from the same task type within that batch.
So a sparse reward task only gets feedback compared to other sparse reward tasks.
Right. This isolates the reward variance, and it provides a much cleaner, more accurate advantage signal. It makes the feedback specific to the cognitive challenge being attempted.
Which their ablation study confirmed was highly effective.
Immensely. It yielded strong gains, especially on the hardest multi-hop benchmarks. So that solved half the stability equation, balancing the data and normalizing the reward intelligently.
But the second part deals with the chaos of the learning signal itself, those runaway gradients from highly exploratory or just plain erroneous outputs.
Right. And that brings us to adaptive entropy-controlled policy optimization, or AEPO.
Tell us about the underlying observation here. What did they find?
The key observation was a nearly perfect statistical correlation. They found a Spearman's rho of 0.96, which is nearly 1 between high-entropy tokens and disproportionately large gradient norms in the negative learning samples.
Wait, okay, let me simplify that for everyone listening. High-entropy tokens are when the model is basically unsure what to pick next. It's taking a wild exploratory guess.
It is.
And if that wild guess leads to a bad answer, the resulting penalty from the RL system, that gradient update, is massive and destabilizing.
It's a runaway process. The model takes a big, uncertain leap that lands incorrectly, and the RL penalty pushes the parameters way too far, risking a catastrophic shift in the model's competence. They realized they needed a dynamic governor to control this exploration-exploitation trade-off.
So what does AEPO actually do to control this? How does it work?
It dynamically monitors the batch-level policy entropy, which is just a measure of the model's overall randomness or certainty. They set specific high and low bounds for this certainty level.
So if the model starts guessing too wildly, the entropy goes too high.
And when entropy exceeds that high boundary, AEPO steps in and it masks all rollouts that have negative advantages.
So what does that mean in practice?
Essentially, the model is updated exclusively using positive, successful samples. It literally stops learning from its mistakes when its guesses are too wild. It functions as an advantage-weighted online rejection sampling.
It's forced to exploit only what it already knows works.
Exactly, which immediately reduces randomness and entropy, and it enforces a more cautious kind of learning.
So the analogy here is that if the model takes a wild guess that turns out wrong, AEPO prevents the penalty from causing a massive destructive overcorrection. It enforces cautious, measured learning. It's like putting training wheels on.
Precisely. And then conversely, if the model gets too confident or too risk-averse, the entropy drops too low, and you risk what's called entropy collapse.
Where it gets stuck in a local optimum.
Right. In that scenario, the negative gradients are automatically reintroduced. This encourages the model to explore again, preventing it from getting stagnant. This dynamic control is why AEPO yielded a significant 3.29-point average gain over the pure GRPO baseline. It provided the stability bedrock they needed for true scale.
That's a really comprehensive solution. They solved the data complexity problem, and they solved the training chaos problem.
Yeah.
But let's move to part 3. Because even with 120,000 tokens of context, you eventually hit a wall.
You do.
So how does QwenLong-L1.5 tackle inputs that are truly ultra-long, the 4 million tokens you mentioned, which are just intractable for standard full attention mechanisms?
They utilize a memory-augmented architecture centered on the memory agent paradigm, and the conceptual leap here is vital. They stop treating long context reading comprehension as a single brute force input pass.
And instead,
they reframe it as a sequential decision-making process.
This is the reading a very long book analogy. You don't try to read all 1,000 pages at once. You read a chapter, you pause, you summarize, you update your mental model of the story, and then you plan what to look for in the next chapter.
That's the perfect description. The long document is processed in these manageable chunks. At each step, the policy model observes the chunk, integrates it with its previous states, and updates a concise, refined memory.
And it's not just memory, right? There's a planning component.
Crucially, yes. Alongside the memory update, the agent generates a navigational plan for the next chunk.
So the model isn't just reacting to information. It's proactively planning its path through the document, deciding where to focus next. It's effectively folding the global context into a compact, actively maintained, and searchable representation.
And this entire iterative cycle of memory update, plan generation, and then the final answer synthesis is all optimized using the same trajectory level RL they refined in part 2 based on the correctness of the final answer.
Now, this leads directly to the progressive fusion training paradigm. If they have a great model, the full context one, and a great memory manager, the memory agent, why can't they just mix the two training data sets together and call it a day?
Because mixing the two training styles, the sequential memory management and the single-pass full context reasoning, it just causes significant damage to both efficiency and stability.
How so?
Training the memory agent, which is specialized in that iterative processing, inevitably degrades the single-pass, full-context reasoning ability. It's a classic specialization trade-off.
You gain the iterative memory skill, but you lose some of that brute force direct attention performance.
Exactly. To solve this, they implemented this specialized multi-stage approach. It's a sophisticated process of specialization followed by consolidation.
Walk us through this architecture because it's really key to their ultra-long success.
Okay, so first they run 3 extensive stages of full context RL training, and they progressively increase the maximum input length up to 120K tokens. This maximizes the model's single-pass reasoning skill on their complex synthetic data.
So this ensures peak performance within the physical context window that the GPU can handle.
Right. Then comes the specialization stage, a dedicated memory management RL stage. They train an expert model specifically on the iterative memory tasks, so the 4 million token problems.
And as expected, this memory expert becomes excellent at sequential processing.
But it sacrifices some general performance.
Exactly.
And this is where the fusion happens. How do they recover that lost general performance?
They use a technique called the SCE algorithm, which stands for structural connection editing. It's a powerful technique for model merging. This step fuses the specialized knowledge of the memory expert model with the high-performing generalized knowledge of the full context model from stage 3.
So it's essential to recover the general full context performance that dropped during the specialization.
It is. It's like merging 2 highly specialized software branches back into the main high-performing trunk.
So they create 2 specialized brains They fuse them, and then they refine the resulting hybrid model. It sounds incredibly efficient. The final step is a final full-context RL stage, stage 4, for ultimate refinement and policy alignment. And the results on the ultra-long performance benchmarks, they validate this framework entirely.
Looking at the corpus QA4M token subset, that is an ultra-long task that no traditional full-context LLM could handle. What did they achieve?
QwenLong-L1.5, operating in its memory agent framework, achieved a score of 14.29. Now, while proprietary systems are still pushing the envelope, this result proves the framework's ability to perform complex, multi-hop reasoning far beyond the physical limits of current full-context attention.
And compared to their own baseline.
They maintained a substantial gain of almost 10 points over their own agent-based baseline on the 1M to 4M token tasks. This architecture successfully unifies the model's single-pass prowess with its iterative memory-based approach.
So what does this all mean for you, the listener? The key question, I think, is whether this entire systematic process, the complex data, the stabilized RL, the fusion, is just a specialized trick for benchmarks, or if it fundamentally improved the model's overall intelligence. Did the complex training actually generalize?
That's the most exciting finding in the paper, I think. They meticulously tested for generalization, and not only did the model successfully avoid catastrophic forgetting,
Meaning it didn't get dumber on other tasks.
exactly, it maintained stability on out-of-distribution benchmarks. But more importantly, the hard-earned information synthesis skills actively transferred to general reasoning-intensive tasks.
We're talking about tasks far removed from reading scattered documents, right? Like high-level abstract mathematics.
Exactly. The model showed clear gains on abstract reasoning tasks. The highly competitive AME-25 saw a 3.65-point increase, and the comprehensive GPQA Diamond saw a near 1-point increase. These aren't just statistical noise, these are real gains in core intelligence domains where foundational strategic reasoning is tested.
Let's take a deeper dive into that AEME 2025 math problem case study they included, because this is where we can really see the inner mechanism of that intelligence transfer. The problem is complex algebraic modeling, finding the sum of 3 positive real values of k under some specific counterintuitive conditions for a function.
Right. And the baseline model, Qwen330b A3b thinking, it failed. It failed because it followed a standard but ultimately wrong pathway. The paper notes that the baseline model got stuck on a purely qualitative calculus approach.
Just trying to define local minimum intervals.
Yes, and it eventually just resorted to a heuristic guess based on fixed roots, which led to the wrong numerical answer. It was just pattern matching its existing knowledge about calculus problems.
But the QwenLong-L1.5, having been so rigorously trained on dispersed knowledge integration and synthesis, follows a completely different, much smarter path.
This is the critical part. The L1.5 model demonstrates metacognitive checking. It actually pauses and recognizes a logical contradiction.
What's the contradiction?
A standard interpretation of local minima usually yields continuous solution intervals for k, but the problem explicitly states there are exactly 3 discrete values.
So the model essentially says, wait a minute, the standard way to solve this doesn't fit the constraints of the problem. My initial interpretation must be wrong.
It's using its synthesis skill to recognize a logical flaw in the expected solution path. It's amazing.
And this discrepancy triggers a what? A reevaluation.
A necessary hypothesis refinement. It reinterprets the geometric condition as a global minimum attained simultaneously at 2 distinct points. This is a complete strategic pivot. It shifts its strategy instantly from that qualitative calculus to algebraic synthesis.
And then it solves the problem.
It then constructs the sophisticated polynomial identity px minus mx equals squared times squared to solve the problem analytically. It gets it right.
That is just profound. It implies that the training forced the model to look at scattered constraints and contradictions across long distances in documents, and that skill transferred directly to recognizing high-level logical contradictions in abstract algebraic modeling.
The training taught the model to be a better strategic planner and checker.
Wow.
Absolutely. And the generalization also extends to practical AI applications we use every day, particularly in agentic and dialogue memory.
How so?
In the agentic memory benchmark, which tests a model's ability to manage the structured sequential history of an agent's operations tracking past tool usage, outcomes, plans performance, improved across most subtasks, with a notable gain on memory KV of plus 5.80 points.
That tracks. I mean, if you can track scattered facts needed for multi-hop reasoning in a document, you can certainly track key value pairs of past actions in an agent's history.
It's a transferable skill.
Oh.
And finally, in dialogue memory, on Long-L1.5, the success is just undeniable. A substantial 15.60-point gain.
And that's huge for user experience.
It's everything. Maintaining state, recalling key points from 20 pages ago in a chat log, and synthesizing that information into the current response is a core feature for any useful long-context LLM. This result directly validates their entire methodology in its most important application domain.
So it really seems they built a stronger general-purpose reasoning engine by systematically forcing it to read hard, long documents and then stabilizing its learning process.
It's the strongest argument I've seen yet that post-training methodology is now the primary differentiator. It's shifting the focus from raw model scale to training sophistication and curriculum design.
If they've achieved results comparable to flagship proprietary models and fundamentally improved general intelligence, what are the remaining limitations? What should we, the listeners, be looking for next in this rapidly advancing field?
Well, the QwenLong team themselves outlined 4 specific critical avenues for future research, and they're all centered on expanding the data synthesis system and refining the RL framework even further.
Okay, so limitation number 1, expanding data coverage beyond simple question answering.
Right. Their current data largely focuses on QA, which is, long input, short output. They need to expand to scenarios that require long input, long output problems.
What would be an example of that?
Think about real-world synthesis tasks. Chapter-level document revision, drafting a complex investment report from 20 scattered source materials, or tasks orchestrated by autonomous agents that require these extended narrative responses. They also acknowledge the need to move beyond just text and incorporate multimodal data.
That makes perfect sense. Most high-value work isn't just answering a single question. It's about synthesizing a 10-page deliverable.
Exactly. Limitation number 2 is crucial for sustainability. Developing the closed-loop data flywheel. Generating this high-quality, long-context data using external models for validation is incredibly computationally expensive, and it hits API quotas.
So their automation, while brilliant, is currently constrained by outside computational resources.
Right. The goal is to leverage the enhanced QwenLong-L1.5 model itself as the data generator and validator.
Use the model to teach itself.
Once the model is smart enough to handle these complex tasks, it can create vast quantities of new QA pairs and, critically, it can generate the correct thinking trajectories for verification. This self-improving closed loop is the necessary next step to accelerate data scaling cost-effectively and move away from that external dependency.
The model becomes its own high-level curriculum creator, ensuring an endless supply of high-difficulty homework.
The third limitation brings us back to the nuances of reinforcement learning. Granular credit assignment for thinking trajectories. We talked about how AEPO stabilizes training, but the reward assignment is still sequence level. The entire reasoning path just gets one single score.
Meaning, if a complex task involves 100 thought steps and 99 are correct, but the final one is a fatal error, all 100 steps get penalized equally, which is wildly inefficient for learning.
Terribly inefficient. They need token-level credit assignment within the reasoning trajectory. This would precisely differentiate the contribution of each individual thought, each planned step, or each retrieved fact. This would allow for much more precise and efficient policy updates, giving credit where credit is due, even mid-trajectory.
And finally, the fourth direction addresses the growing subjectivity of tasks, sophistication of the reward model.
Right. Current rewards rely on simple rule-based checks or using another LLM as a judge for correctness. And this works perfectly for objective, factual QA.
But for more open-ended and subjective tasks,
like creative writing or strategic recommendation or legal drafting, correctness is multifaceted. The future direction is developing LLM-based rubric reward models.
So instead of a simple binary correct or incorrect reward, the reward model would actually score the response against a detailed, multifaceted rubric.
Things like coherence, originality, adherence to a specific style guide, tone, all of it.
Precisely. This provides a much richer, more nuanced feedback signal, which will better align the agent's behavior with complex human preferences in these real-world subjective scenarios where there is no single right answer. This has been a true deep dive into the engineering of modern AI reasoning. Let's try to recap the key takeaways for you, the listener.
I think the biggest one is that the advancement of long context performance is shifting dramatically. It is no longer simply about building a bigger physical context window or scaling pre-training data. The focus is now on the refined training methodology, that post-training recipe.
And the QwenLong-L1.5 recipe demonstrates this power by combining three specific necessary elements.
Yeah.
Systematic, complex data creation via structural synthesis using knowledge graphs and SQL.
Drastically stabilized reinforcement learning using algorithms like AEPO to manage those chaotic gradient signals.
And the fusion of powerful, full-context reasoning with an iterative memory agent for that ultra-long context handling.
And this unified approach led to these substantial gains, especially on the hardest reasoning tasks. It proved that teaching a model to synthesize information over vast contexts provides a foundational boost to its general-purpose intelligence.
We saw strong evidence of this in the improved strategic thinking, in the math problem solving, and the enhanced dialogue memory. The focus is really shifting from the question, how much context can it hold, to how intelligently can it process that context,
That's a new frontier.
which raises the final provocative question for the road ahead. If the complexity of data synthesis now demands a multi-agent system of proposers, solvers, and verifiers, and the necessary next step is creating a closed-loop flywheel where the high-performing model becomes its own data generator and thinking trajectory validator, are we witnessing the moment where high-performing LLMs become fundamentally self-accelerating?
It means that the high-level LLM is increasingly taking over the design and the optimization of its own curriculum. It changes not just how models learn, but who or what teaches them.
The ultimate self-improvement loop. Something for you to mull over as you see these models deployed in your own applications and tasks. Thanks for joining us for the deep dive.